Okay, welcome. Uh, any questions, comments before we start? Any related thing? I think this is where we finished up last time, and we went on a discussion, and things are fine. Okay. Okay, let's move forward. I think now let us get to what are reactive species. Okay. For the fun of it, the definition of reactive species is nebulous. Okay. So, there is no clear cut definition, it is some understanding that we can work with. That is the way the field is, we cannot do much. Okay. I do not like it either, but that is the way it is. Okay. For definition it is, I will tell you why it is rather nebulous. It is more of an understanding that one becomes comfortable with experience rather than a clear cut definition. In general, reactive species are supposedly highly reactive molecules. That is how the name kind of came about, and most of them are. Okay. Almost all of them are highly reactive. However, that does not cover the entire gamut. There could be a drastically wide variation in their second order, excuse me, second order reaction rate constants. Okay. If you recall basic chemistry, reaction rate constants give you an idea of the speed of the reaction. In this case, it goes all the way from 76 per molar per second, this is second order rate constant, 76 per molar per second to 10 power 11. Okay, it's 10 orders of magnitude, huge variation. Okay. And I'm not choosing some odd reaction. This is for a reaction that is highly popular. Okay. The so-called classic Fenton reaction, where hydrogen peroxide reacts with iron, which you will become familiar with. We will see it so many times, you will become familiar with. Okay. You do not have to memorize anything for this course. Anyway, there is no need to memorize also. So, through repeated exposure, some will become a part of you, that is fine. And some of you of course have good memory, that is good, very good to have. You need not necessarily have it. So, there is a wide variation in the reaction rate constants involving reactive species, and that is what it is, right. So, please keep this in mind whenever somebody talks of reactive species and why is it not free radical, why is it this thing. We saw in the last class, I think it was initially called free radicals, and then it was called reactive oxygen species alone, and then people realized there could be other reactive species that do not have an oxygen background, or they are not derived from oxygen, and so on. Let us look at some examples of common reactive species. The ones that are derived from oxygen are called reactive oxygen species. Okay, again, do not take this too strictly, I will give you some oddities right away. This is fine, hydroxyl, there is a dot there, OH, superoxide, O2 dot minus. You might want to write these down, because these are something that you will encounter many times. So, hydroxyl certainly derived from oxygen, superoxide certainly derived from oxygen, and many other things are typically called reactive oxygen species. Reactive nitrogen species, RNS, are the ones derived from oxygen. Some classic examples are nitric oxide, which play a lot of physiological roles, NO dot, right, peroxynitrite, ONOO minus, and so on and so forth. If you see here, you have oxygen here also, okay, as an important part of a molecule, right, but this is typically not classified as a reactive oxygen species, it is classified as a reactive nitrogen species. So, that is the practice, nothing else. Similarly, derived from sulfur, it is called reactive sulfur species. Thiol radical is a very good example, RS dot, and so on and so forth. Might want to write at least these 6 down. By the way, I forgot to mention, I might get a call. Okay, I will go out and take it. That's why I've kept it on mute, but I'll need to attend to that. It's easier to see it here. No? Okay, let's move forward. Right. You have a dot here, you have a minus here, you have a dot alone, you have dot and minus together here, and so on. Okay. So, what does the dot mean and what does the minus mean? Any idea?
Dot means a free electron.
Dot means a free electron. Yeah. Okay. Yeah, that's fine. We need to understand it a little better. That's true. Minus?
Lone pair of electron.
Lone pair of electrons, maybe. So, what's the difference between a free electron and a lone electron or a lone pair of electrons, apart from the pair part of it?
Like in electron configuration, electrons has to be paired, but at times electrons doesn't have a pair, which has to be donated or something.
That is what he meant by free electron. Okay. In the orbital, orbital means energy levels. You have one electron that is separately sitting without its opposite spin pair. That is the meaning of dot. Okay. So, minus is rather mundane.
Needs to accept electrons. Like the meaning of it is like that.
Needs to accept electrons. Think of other things.
To complete the octet.
To complete the octet. Any other guesses? Yeah, we are guessing. We'll be wrong, so it doesn't matter. So, let's feel free to guess. That's the whole point.
Additional extra
Additional to what?
electrons. Additional electrons
Additional electrons with respect to?
in the orb.
Right. Can you define it a little better? Yeah, you're right. Whatever you said is right, but can you define it a little better? Typically, in a molecule, the number of electrons equals the number of protons, uncharged molecule. If the number of electrons is one or more than the number of protons, then you put in a minus. Okay. Even if there are two more, you put in just a minus. You don't, I mean, sometimes you put a 2 minus and all that. Again, this terminology is very iffy, okay, as will become clear right away. But this is what it means. Whenever used, it means that this is an unpaired electron, okay, free electron. Therefore, you expect it to be a little more reactive, a lot more reactive. And a minus means the number of electrons is more than the number of protons. So, to understand this, let us look at atomic orbitals. You all know the Aufbau principle, right? The orbitals get filled in the increasing order of its energy levels. So, I think 3D comes after 4s or something like that. I think that is where the numbers start moving out from the orbitals. So, if you look at one set of outer orbitals alone, the two orbitals, there is a 1s orbital, there is a 2s orbital which comes above that in the energy level. The probability of finding an electron is kind of spherical in all these s orbitals. The probability of finding an electron is a dumbbell kind of a thing. In the case of p orbital, the probability of finding it's a little more complex, double dumbbell and so on and so forth in the case of d orbitals, right. You recall that. We are not going to do all that, we are not going to work at that level, but we will work at these levels, the outer orbitals. You know, beryllium, boron, carbon, nitrogen, oxygen, one group of relevant compounds. So, 2s2 is this, 2s2, 2p1 is this, 2s2, 2p2 which is carbon is this, right, beryllium, boron. Nitrogen is 2s2, 2p3, there are 3 electrons unpaired. O is 2s2, 2p4, right. So, this is the atomic orbital of that of the atom, right. If you write the, let us focus just on the oxygen, if you write the complete electronic configuration, you have 1s2, 2s2, 2p4, 8 electrons. So, that takes care of that, right. So, the relative energy level, this is not to scale, of course, is this. You know this, that the 2s2 is much lower than the p orbitals, 2p orbitals. So, that goes like that. And if you put 2 atomic orbitals, you will get a you put multiple atomic orbitals, you will get a molecular orbital, right. You may not have done molecular orbitals much, but at least let us just touch some part of it without getting into the quantum aspects. So, if you have 2 atoms of oxygen, okay, just one atom of oxygen 2s2 2p4, another atom of oxygen 2s2 2p4, these combine to give you a set of molecular orbitals. Orbitals are essentially energy levels, quantized energy levels in which the electrons will stay. So, you have sigma bond orbitals and pi orbitals bonding, anti-bonding orbitals, and so on and so forth. So, this is the energy level with which it goes: sigma 2s, sigma star 2s, then sigma 2p, pi pi 2p, pi star 2p, and sigma star 2p, and so on and so forth. Okay. Fine. So, from an atomic orbital, you get a molecular orbital by putting these 2 things together. That is good enough, even if you have not looked at these things in great detail. If you look at the molecular orbitals, we look at just 3 to begin with. If there is some problem, you need to come down to this, and that is the only reason why it is given. We will not work at this level in this course. Okay. So, you do not need to know manipulations and so on and so forth. Actually, you need quantum aspects to even manipulate. We are not getting into that. We will stick to classical aspects in this course, and therefore, but this is where it all starts from. So, if you have, these are fine, the 2s levels are fine, the 2p levels still here are fine. Let us focus on the pi star orbitals. You have one with one spin and the other in the opposite spin in 2 of these separate orbitals, you get something called a singlet oxygen, okay, which is, if you look at this, in an oxygen molecule, both these spins are in the same direction. Singlet oxygen, both these spins are in opposite direction. Singlet oxygen is a lot more reactive than oxygen. Same formula. Okay. Superoxide, you have one more. Okay. One more, and it is unpaired. Therefore, you have a dot here, right. You could ask the question, it is unpaired here, but you do not have a dot here. It is unpaired here, but you do not have a dot here. That is customary. Okay. Strictly speaking, you should put in a dot, but nobody puts in a dot. So, we also do not put in a dot. That is as simple as that. Okay. So, if it is there, you are sure. If it is not there, you are not sure. You will have to go back and check. So, the superoxide has one extra. This is far more reactive. Peroxide is all filled. Therefore, it is not as reactive as the others. It is also reactive, but it is not as reactive as the others. Okay. So, take a look at the pi star orbitals, and that is the essential difference between molecular oxygen, something called singlet oxygen. By the way, there are 2 forms of singlet oxygen, where I think both these are in the same orbital, in the pi x star orbital, both these electrons, and one is left unfilled or something like that. There is a difference. And then you have superoxide, which you will see many times. This is the molecular configuration, the electronic configuration of that, and peroxide, where you have all 4 filled. Any questions? Just for information, yeah.
So the reason for the single dot is in the superoxide is because of the
Unpaired electron. Unpaired electron, and minus is because if you count the number of electrons, it will be one more than the number of protons. So, the molecule has a net charge. So, the charge in the molecule is indicated by the minus, the net charge in the molecule, and the dot indicates whether you have an unpaired electron or not. Any other question? Good. Okay, this is from your book, I think the older edition of your book, and they have taken it from Encyclopedia of Life Sciences and so on. So, this gives you some examples of reactive species. It is categorized as radicals and non-radicals. Radicals are the ones that have an unpaired electron, non-radicals do not have an unpaired electron. You have tons of examples of each. Okay, so that is the reason why they changed the name from earlier name from free radicals to reactive oxygen species at least. So, reactive oxygen species, we already seen superoxide, hydroxyl, peroxyl, alkoxyl, hydroperoxyl, and so on and so forth. Reactive nitrogen species, nitric oxide, nitrogen dioxide, we also saw peroxide nitride, and so on. Non-radicals, hydrogen peroxide, HOCl, HOBr, ozone is also considered a reactive species. Singlet oxygen, one form of it is given here, and nitrous acid, and so on and so forth. Okay. There are many, as and when you come across, see whether it's categorized as a reactive species in the source. That's all. There's no other way of finding it out. Typically, if the reaction rate constants are very high, the very high chance that it is a reactive species, 10 power 7 and more, it's certainly a reactive species. Okay. Now, can you do this exercise about take about 5 minutes? Identify the following species with all the relevant tags among each one you categorize, is it a RS, is it a ROS, is it a free radical? Go and do any search that you want, search the net, and I've given you some background. With that background, you search the net and figure out what this is, and then let's discuss. 5 minutes.
Free radical and reactive species are the same thing.
Yeah, one could have many tags. Each one of these could have multiple tags.
No, but by definition, are these two the same?
No, historically these set of molecules were called free radicals in the 50s, 60s, and so on. Quickly, people realized that you cannot really call them free radicals. There are so many non-radicals that are reactive enough to be considered under this category. So they changed the name to reactive oxygen species. For about a decade or so, they were called reactive oxygen species. And then people slowly realized that no, you have all these nitric oxide and things like that, which are also, can come under this category. So from later part of the early 2000s, that decade, people started calling them reactive species, and it was formalized in the textbook edition, 5th edition of Halliwell and Goodrich that came out in 2015. So from that time onwards, all of us call everything reactive species.
Yeah, but the thing is, you are differentiating between reactive oxygen species and other reactive species which are not oxygen species.
Right.
So, my doubt is between reactive species and free radical.
I know. Some reactive species could be free radicals. Not all reactive species are free radicals. One that have an unpaired electron among the reactive species are free radicals. Yeah, that's the actual. Okay, people. Hydrogen peroxide. RS, ROS. Okay, good. Hydroxyl. It's not a free radical. Hydrogen peroxide is not a free radical. Hydroxyl.
ROS and
free radical and ROS.
And RS. Yeah, all three. Yeah, if it's a ROS, it's definitely RS. So, superoxide. Both. It is no, it's all three. All three. It is a free radical. It has an unpaired electron. Peroxyl is also all. Peroxyl HO minus is there. No, minus is there. It's not a free radical. If it has an O2 dot. No, you don't write 2 minus. Peroxyl is ROO dot. Yeah. Peroxyl, ROO dot. Yeah, it is a free radical. Yes. ROO dot is peroxyl. So that is a free radical. Yes, you are right. RS and ROS. Singlet oxygen. It could be a free radical. It could be a free radical depending on its form. There are two forms. One is a free radical, other one is not. Okay. Then peroxynitrate. RS. Good. Oxygen.
It's not, it won't fall any free of this category.
Why?
It's not
It is RS, it is ROS, it is free. It is quite reactive. Oxygen is very reactive. O2. Yeah. Oh, you're talking of nitrogen. You're talking of nitrogen or you're talking of oxygen? Oxygen is certainly a RS, it is certainly a ROS, it is certainly a free radical. Only thing is that we don't indicate any of those. Rather, we don't indicate the free radical part. Nitrogen molecule, of course, all three are not there. It is neither RS nor ROS nor a free radical. Nitric oxide, RS definitely, and nitric oxide NO dot, right? NO dot, right? That's nitric oxide, right? It is a free radical. Okay. Hypochlorous acid.
It is ROS,
Okay.
but not free radical.
Yeah, it's not a free radical, but it is RS and ROS. RS just because it's I mean anything RS, RNS, anything becomes a RS. So peroxynitrite is also RS certainly. Peroxynitrite is considered RS. I'd given it as example of one of those. It's not. It's typically classified under RNS. This you'll gain only by experience. You won't know. You cannot guess beforehand because there's enough oxygen sitting there. But you call it RNS, and it is peroxynitrite is not a free radical. It has a negative charge. Yes, ONOO minus. Right. So it has a negative charge. I think we. Yeah, peroxynitrite ONOO minus. So it has a negative charge, and but it doesn't have a free electron or an unpaired electron. Therefore, it is not a free radical. Good. So you're getting warm, and you continue with this. Keep checking as things come along. That should be fine. I think I'll close this. I wanted this open for some, or I should close this particular program, I suppose. Okay, nothing important anyway. Okay, now let us get into some history of oxygen. We'll have a long introduction, okay, but that is good. You'll get to hear a lot of relevant stories. You'll get an overall picture, which is nice. So, some history on oxygen, very interesting history. You may know that there was no oxygen when the Earth began, okay, 4.6 billion or 4.8 billion years ago. There was no oxygen in the atmosphere, right? Initial organisms which were anaerobic appeared about 3.5 billion years ago. And about 2.5 billion years ago, cyanobacteria or blue-green algae, they acquired the ability to split water for photosynthesis, and thus you know that photosynthesis releases oxygen as a part of the electron transport process and so on and so forth. So, water gets split into hydrogen and oxygen. The oxygen here from water gets released in copious amounts. Okay. And this is believed to have been the source of all oxygen on Earth. Okay. Right, a majority source even today, and this is why the oxygen levels began to rise in the atmosphere. There were some very nice videos which you may want to look at. I don't think I've marked any here, but that's okay. Let us get an idea of some time scales and so on and so forth on the side. You know, there are eons. I think we are the third or the fourth eon of Earth. Each eon consists of many eras, and each era consists of many periods, and each period consists of many epochs. That's the way it goes. And these two are given, the links are given on the Moodle page. You might want to check the first one alone. I think it's about 2 minutes or something like that. You won't gain too much. If you want to know more, you can go and look at it multiple times, but you'll get an idea of what we talk about. So, take a look at it, put on your headphones or keep your volume low and take a look at that. It might have some. I'll also take a look at that and come back. Okay, people, you got an idea. Just once is good enough for now. You won't have gotten the import of all that. There are too many terms there. If you are interested, you can go back and look at those terms. It's just to give you an idea and to kind of familiarize you with the names, what it is and what order it is and what exactly happened. You need to go and read them in detail if you have an interest. So this is same thing set to music, which will help you remember it a little better. But that please do it in your own time. It's the same material. Okay. And then this is an interesting video which covers something that we talked about now, how the oxygen levels in the atmosphere increased. Please take a look at this video. Slightly long, but worthwhile. Please take a look at this video, Earth and the early atmosphere. Anybody else not on Moodle? I think all of you. You're also not on Moodle. How come? No, I've had it.
One more G course has to be rejected so that it will be added.
Oh my goodness. So what I'll do is I'll send this file to you because for her I can add right away. Yeah, you can get it from, you can just download it from one of their accounts or something like that. You'll have the file there. It's a PDF file. If can you ask? I think a WhatsApp group has been set up, right? Radhika said that she was going to form a WhatsApp group. If not, one of you please give the file. See, that file will keep on getting updated. As of now, I think it covers about 2 or 3 chapters. So one of you please forward that, download that file and forward it to him so that he can do that. Yep, please. Please take care of that, otherwise it will come back to haunt you later and so on and so forth. If the records are not proper, your name won't show up on the course list. Your name shows up on the course list. Moodle, it's not able to update. Okay. Now, for now, it's okay, but this will come back to haunt you, especially when the grades are given. So, clear it up right away. Yeah. This may not, actually only Moodle is a problem, right? Only Moodle is a problem is okay. Academic, have it clean.
The workflow, they are waiting for that slot to get rejected so that this can.
Workflow, you'll have to clean it up. Establishing that this has actually happened. And then the average value is given as a solid line, and these are the confidence levels and so on. Okay. So then it came down, okay, around 250 million years ago, and then it has kind of went up and it has stabilized. Okay. There are reports that during this period, the dragonflies were about a foot in size and so on. Now dragonflies are this much, right? The dragonflies sizes during the time when the oxygen was around 35% in the air was much larger than this. There are evidences for that, such things have happened. What is more interesting is this percent carbon dioxide was at the same time. Okay. Note then when we started out, it was 0.5%, rather 600 million years ago, it was 0.5%. Okay. Of course, it has come down, and here there's a lot of the 0.01% makes a huge difference now, we realize, in terms of global warming and so on and so forth. Of course, the earth has seen a lot of cataclysmic events during this time, and now we are around here 0.03 till sometime in the last century, and now it is 0.04 is accepted. That's a big change, not done, and so on and so forth. Okay. Have you thought about the trees around, the wood around, okay, or especially IIT? What's the source of carbon and all that? CO2, nothing else. It doesn't get it from the earth. Okay, it gets some minerals from the earth and so on and so forth. All carbon comes from CO2. Okay, so that gives you an idea of how much carbon dioxide, and predominantly present as carbon dioxide. Okay, so that kind of gives you an idea. And also, I do this exercise in my introductory classes to undergraduates. calculate the mass of air in this room. Okay. Um, with tiles, you can easily count. This is probably about 4 feet each one, maybe 3 feet, let us say. So 1, 2, 3, 4, 5, 6, 7, 8. 8 into 3, 24, or leave out that part, about 20, and this would be 1, 2, 3, 4, 5, 15, 20 by 15 feet converted into meters. The density of air is what? Yeah, these are numbers that are good to be known as thumb rules. It turns out to be 1.29 kilogram per meter cubed. Okay. Water, of course, is 1000 kilogram per meter cubed. All right. One gram per cc, you convert that into kilogram per meter cube. There's a meter cubed here, there's a kilogram there, so work it out. But air is definitely 1.29 kilogram per meter cubed. So with that, you can work it out. Okay, work it out, and you'll be surprised. I think we need to stop now. We will stop, and just the last point is there are isotopes of oxygen present. We are focusing mainly on oxygen here. Oxygen 16, which is the normal one, is apart from oxygen 17.04% and oxygen 18.2%. That's good to know. Okay, when we meet on Monday, we'll begin with some more interesting properties of oxygen and so on and so forth. Be prepared to break some perceptions that have been ingrained in you and so on and so forth. Some, not many, when we meet on Monday. Any quick questions, comments?
Why there is an increase in oxygen and decrease in oxygen during 200 to 300?
I have forgotten. I did read it about 11 years ago. I have forgotten, but it is known, or at least the evidences are there as to why it increased and so on and so forth. I'm not too sure.
Wasn't it because of cyanobacteria?
The cyanobacteria initially.
Yeah, because of it increased first.
But why did it increase so much? Or rather, that period alone, why did I don't know. I don't recall. Listen. Yeah.
Like, is the human height is related to the oxygen levels in the atmosphere? Because in earlier times, people used to be around 7 feet, 8 feet.
There are some records, yes. I do recall some people being tall and so on and so forth. Not all. Not all over the world.
Around 6 feet was the normal height. But and as there are predictions like in future the height will be the people will be very short. There is predictions for future. So maybe it is the reason because oxygen is depleting in the atmosphere.
It doesn't fit in, right? The correlation itself is.
So just like you told that dragon.
Yeah, dragonflies are no. Yeah.
1 feet.
Yeah.
Oxygen was very
Very high. Whether the humans, I mean, this was what, only million years ago. We came in only 65 million years ago, so that is around here. Humans came only here, so humans have not seen these levels of oxygen at all.
It is decreasing from
Yeah, it is decreasing from this time, but it is decreasing from 0.05 to 0.03. That is the decrease that has happened. Now it is increasing to 0.04. This was before that. I think the data was before. Yeah, this is 1995, right? So before all that thing became big, climate change and so on, so forth became big. Although people knew these things in 1995, there was not much of an awareness. Not too sure, but then again, the times don't seem to correlate well. You might want to think more about it. I definitely know that dragonflies were about a foot. I mean, I read that dragonflies were about a foot in size during this period. Whether it also translates to humans, I don't know. Rather difficult. I don't have evidence. So please check. If you come across incontrovertible evidence, please present it to the class. Let me know. You can present it to the class.
So is that because of the formation of ozone layer and then the oxygen started building on, and then once there was sufficient oxygen, so other things, organisms and all which were there, the earth, they started consuming it on, and there was
Then why did it go up at all? Yeah.
because the ozone was there, so it started trapping on the oxygen, like it was not flying, like escaping. So it was not like
I don't know. No, they don't escape here. It's not easy to escape. There's gravity, so Earth's atmosphere remains because of gravity. So that I don't think is escaping is. I don't think it's a thing. Now we'll have to really stop because there might be another class. Let us continue this discussion if there is enough interest in the beginning of the next class. Okay. Okay, people. We'll meet next on Monday at 12.